All right, class, let's continue with the applications in 3.3. So one of the problems we had been doing all along is finding the equation of a tangent line to a graph at a certain point in time. So we're just going to do one more of those problems. This time it's about the function that's a logarithmic function. So fine. How do I find, again, the equation of a tangent line? Well, the equation of a tangent line is going to have to do what? Y equals to mx plus b, right? Okay. So y equals mx plus b, great. So to come up with the equation of a line, I'm going to need the slope, and I'm going to need a point. Okay, so how do I find the slope? Well, the slope is the derivative of this function. Now, where exactly do I want this tangent line to be? I don't want the tangent line to be in general at any point x. I want it specifically when x is e. So that's the value, the x value that we're going to plug in here, yes? Now, sure enough, we first have to find the derivative in general. So the derivative of a log function is 1 over whatever's inside it times, move in and take the derivative of the inside function, which is 2x. So simplifying this, I'm simply going to get one of the x's goes away, so that's 2 over x. Great. Now it says I want specifically the slope when x is e, so I'm going to plug in e, and I'm going to get 2 over e. So this is the slope of this line. Great. Now I need a point. What point do I use? Well, again, I use some point of coordinates x comma y. What's the x value given to me? E. What is the y value? Well, the y value is the function value when x is e. So what is that going to be? Oops. If I plug in a e into this function, f of e is going, let me put it here down below or up above. F of e is ln of e squared. So remember, an ln and an e cancel each other out, and I'm left with just the 2. Okay. Sure enough, one other way of looking at it is, because remember how you can take out an exponent outside of a log? So you can take down the 2, and ln of e is equal to 1, so 2 times 1 is equal to 2. There you have it. Okay, so we have the point, we have the slope. All I have to do is either use this formula right here or use the point slope formula, whichever one you prefer. So I'm going to use the point slope formula. And so I'll have y minus, the y value is 2, is equal to the slope, which is 2 over e, times x minus, the x value is given to be e. So sure enough, simplifying this will get me y minus 2. The SHRIB is 2x over e, minus 2 over e times e is going to equal to 2. So sure enough, when I add the 2 to both sides of the equal, it goes away. So y is equal to, if you want, 2 over e times x, or 2x over e, whatever you want to have it, there it is. Okay. So remember our applications on, just looking for a highlighter here, I don't see, okay. So remember my applications on compound interest formula. So let's read it. It says an amount of $5,000, that's the principal, was invested at a rate of 5%, that's the R. Compounded continuously, again, tells us right away that we're going to use the PERT formula, right? Find the rate of growth, at this amount 4 years and 10 years later. So what does it mean to find a rate of growth? A rate of growth is the speed at which the function's changing. So a rate of growth simply means to find the derivative, yes, of this function. So first of all, let me put all the values in. So the amount in the account is going to, first of all, be 5,000, e to the 0.05 for the rate, yes, times t. So as you see, this is a function of time. Okay. All right, so how do I find the derivative of it? Nothing easier than that. That's what we practiced on. So I'm going to write it here. the derivative of this function is going to equal to what? Well, as always, if you have a coefficient in front of a function, the derivative of some kind of constant times a function, you keep the constant, and then we're moving on to take the derivative of the function, time. So 5,000 times. What's the derivative of a e function? Is itself times, still move on and take the derivative of the inside function, which is the power. So the derivative 0.05 times t is simply 0.05. Okay, so I'm going to put this together. 5,000 times 0.05 should get me 250 e to the 0.05t. And there you have it. That's the derivative. So that's how fast this amount is changing. Okay, now it says, find the rate of growth of this amount 4 and 10 years later. So in other words, find this derivative specifically at 4, and then find this derivative specifically at 10. Okay, so plugging in a 4 into this derivative function will get me $305.35. And plugging in a 10 into this function will get me $412.18. Okay, so what does that mean, that the rate of growth 4 years later is $305.35? What this simply means that after 4 years, the amount in the bank is going to increase by $305.35. So that's the growth for the 4th year. So it grows from whatever it was after 4 years to whatever it's going to become after 5 years. The difference within that year is $305. Now, whereas 10 years later, the amount is growing by $412.18 per year. So the difference between the 10th and the 11th year is about $412.18. So sure enough, the money grows more rapidly in time because, again, remember what I said, your interest starts earning interest. And as you accumulate or accrue more interest, obviously you're going to gain or earn a lot more on that interest as well, right? So the amount keeps changing at the beginning of the year, right? Because now you are to this amount, now this amount is growing, now you got to this amount, now this amount is growing. So the amount of growth is larger and larger. Okay. It says the world population in billions is predicted to be so and so, where T is years since 2017. Find the projected population in 2050 and the instantaneous rate of change in 2050. So instantaneous rate of change, again, is the rate of change, yes, so the rate of growth or decay, who knows. So that instantaneous rate of change, again, means to find the derivative, yes. Okay, so the function is given. We don't have to set it up this time at all. T is years since 2017. Let's see, it says find the projected population by 2050. So by 2050, I'm not going to plug in 2050. Why? Because T is years since 2017. So how many years have passed since 2017? By 2050, well, that's 33 years, right? So it's the 33 that we're going to plug in. So 7.6 e to the 0.0077 times 33. Plug this into your calculator, and you're going to get to about 9.8, and it's in billions, right? So not 9.8 people, but 9.8 billion people. All right. Now it says, find the instantaneous rate of change by 2050. Well, to find any instantaneous rate of change or rate of change means to find the derivative. Okay, so same as in the problem above, there's a coefficient of 7.6, which I'm going to keep, times the derivative of the e part is itself times, move on and take the derivative of the exponent, and that's just 0.0077, right? Because again, the derivative of some number times x or some number times t is just that number. And putting this together, sure enough, the 7.6 can be multiplied to the 0.0077, and what you will get is a 0.0585 e to the 0.0077t. Good, so that's the derivative. It says find that derivative by 2050. So let's plug in 33 into this derivative function. Okay. And again, put this in your calculator, and that's 0.075. So what does that mean? I'm going to write it down. It means that by 2050, the world's population will be about 9.8 billion people, and it will be growing at a rate, or about by how much? By about 0.075 billion. 0.075 billion multiplied by 1,000 is about 75 million people per year. So that's what it reaches, the amount that it would reach by then, and it's projected to grow by that year by another 75 million people. Okay, so that's that, according to that function, which of course these things change all the time. Okay, so let's get to more applications. It says, this time it's a logarithmic function application. It says, a company spends X, and this is in hundreds of dollars, on an ad campaign. The amount of money made in sales can be modeled by this function. Okay, it says, find the amount of sales after $300 was spent on advertising. So for the first part, all I have to do is plug in 3. So it says, a company spends X $100. So if it says $300, X is 3, right? So it's 3 in hundreds of dollars, right? So 3 is what we're going to plug in. So all you have to do is just put this in. So put in your calculator, and you're going to get this amount. So what this simply means is that when you spend $300 in advertising, we're expecting to make $10,000 and $10,204 in sales. Okay, it says find the derivative at 3 and interpret the answer. So first of all, let's find the derivative, period. So the derivative of 500 is going to be 0, right? It's a constant, plus 7,000 stays times the derivative of the ln part is 1 over x plus 1. So it should be 7,000 over x plus 1. Okay, so plug in the derivative at 3. So that's simply 7,000 over 4, right? Which is about 1750. So that simply means what? That when $300 was spent on ads, yes, the amount of sales will increase. I have no room. By how much? By $1,750 for every what? Extra 100 spent on ads. Okay, so again, for every 1 unit of X, and 1 unit of X, one more time, is hundreds of dollars spent on an advertising campaign, right? So the amount of sales will grow at $1,750 for every one extra 100 you spend in ads. Okay, well, that's the answer. All right. Let's see. It says the price function of selling X amount of units of a certain commodity is so and so. Find the revenue function and find the amount of units sold and the price at which they should be sold to maximize revenue. So revenue, one more time, is what? Number of items sold times the price per item. Okay. So the price is here, and the price depends on how many items you are selling, right? So if you're selling an X amount of units, so if X is the number of items sold, the units, the price per unit is 10 minus ln of X. So there is our revenue function, right? Price times number of units, that's it. And then the same thing in 2.3 for Then the same thing in 2.3 with other different types of functions. So what I would definitely do is distribute this, because sure enough, we want to maximize revenue. And how do you maximize revenue? You take the derivative and set it equal to 0, right? So the derivative of 10x is just the 10. The derivative of x ln x, we definitely need the product rule. And definitely don't forget that to keep it in a parentheses, because you need to distribute that minus. So the derivative of x is 1 times ln x plus, keep x times the derivative of ln x is 1 over x. So that's a 10 minus ln x and minus, that's a 1, right? So combining like terms, that's a 9 minus ln x. Okay. So what do we want to do with this? We want to set it equal to 0 and solve. So when does 9 minus ln x equal to 0? That's when ln x equals to 9. I'm going to turn this into an exponential form. Remember, the base here is e. So e to the power of 9 is equal to x. So I'm going to write this, put in your calculator, and it tells me it's about 8,103 many units. So this is the amount that maximizes revenue. It says don't just find the amount of units, but also the price at which they should be sold. So what's the price? The price is 10 minus ln of x. And what was x? E to the power of 9. I'll keep the exact value. Why? Because ln of e will cancel out. And you're left with 10 minus 9, which is $1 per unit. So that should be the price per unit right there. Okay. All right. And finally, the last question here says the demand function for a certain commodity is. So remember, what is a demand function? A demand function is the number of units that will be sold when the price is a certain number. So D of P is the number of units sold at a price of P. So when you make the price P, then that's how many units will be sold. Okay. Yep, so exactly what I just said here. This represents the number of units the consumers will buy at a price P. Good. Find the expenditure function. Expenditure is the amount spent. So what is the amount spent? How much money are the consumers spending? Well, their spending depends on how many items they're buying, right? So the number of items they're purchasing times the price per item, yes? And again, one way we could look at it as revenue in the pockets of the manufacturers. On another way, we can look at it as money spent out of the pockets of the consumer. So expenditure is really the same thing as revenue. Just looked at it from a different point of view. Expenditure is what's being spent. Revenue is what has been made, right? So the amount of money made. Okay, but it's the same. So how many items are we Buying, well, D of P, right? Number of units, times, what's the price that we're paying? Well, the price should be P, yes? So this time the prices are variable, whereas before the number of units was our variable. So it's really the same problem, looked from a different point of view, right? Depending on the price is how many items we are, depending on the number of items we're selling, we're going to make a price for you. Depending the price you made for us, we're going to be buying this amount of units. Yes. Okay. So, okay, for our function here, I'm going to take a separate piece of paper in a minute. The expenditure again depends on the price that's being charged. So, that is 2,000 e to the 0.03p times p. Okay, so that's the expenditure function. Now, how are we going to find the maximum, right? We want to maximize expenditure. Fine. What we need to do is we need to take the derivative. So, I'm going to take the derivative of this function. How are we going to take the derivative? Well, it looks to me very much like it's a product, yes? So we're going to have to use the product rule. So, here's my first function, or my first factor, here's my second factor. So, take the derivative of the first. What's the derivative of the first? 2,000 for the coefficient, e to the 0.03p, because the derivative of e is itself, times the derivative of the exponent, which is 0.03. Okay? That's the derivative of the first, times, leave the second factor alone, plus, leave the first factor alone, times the derivative of the second factor, which is 1. Okay, so that's the product rule. Okay, so again, that's the derivative of the first times the second, plus, leave the first alone, times the derivative of the second. Okay. So, what do I do with this derivative? We're going to have to set the derivative equal to 0, yes, and solve. Okay. So I'm going to write this one more time. I have 2,000 e to the 0.03p, and I'm going to leave that point times 0.03 and a p, plus 2,000 e to the 0.03p. Okay, and we want to set this equal to 0. All right. Now, remember how in some of the earlier examples, and luckily I have this one right here, how we were left with an e to the x times something plus an e to the x times something, and I said it does help to factor out this e to the x, and that's exactly the case right here, and that's why we practiced. So when you look at these two terms, there's definitely a common factor. One of them is 2,000. The second one is this e value. Okay, now if I factor that out, what's left? A 0.03p plus 1. Okay. Oh, now I noticed. I was already thinking in my head, oh my gosh, this doesn't look good, because I'm going to end up with a negative value. And what I noticed, and I've been wondering about this all along, there's a minus in there that I didn't see because I went over that. So it's a negative, so let me fix that. And that totally makes sense. The higher the price is, the less amount we would be spending. So I'm going to fix that minus. Now, of course, if I take the derivative of a negative 0.03, I'll be left with a negative 0.03 here. Okay, so that's a negative 0.03. That's it. I just picked the minus. Okay, so when is a product equal to 0? Product equals to 0 when either one of the factors equals to 0. Okay, sure enough, same as you might have come up in some other examples in section 3.1 and 3.2, this is never going to equal to 0. Sure enough, you can divide by 2,000. and a value of e will never equal to 0 because exponential functions are strictly positive. Yes, they never turn negative and they never turn 0. There's no value in here that would make an e to that power equal to 0. Okay, but what definitely can be 0 is this expression here. So I'm going to move the 0.03 over, divide by it. So finally, I'm coming up with the price to be about 33.3. Let me see. I haven't, yeah. That's right. So $33.33. So there's the P. Okay. Let's go back and make sure that we've answered the question. It says, find the expenditure function. We did. And find the amount of units sold. That's the amount of units sold, and the price at which they should be sold. The price at which they should be sold is $33.33. The amount of units, well, depends on it this way, right? So what was the demand function? It was 2,000 e to the negative 0.03 times p, which is 33.33. Okay. So put that in your calculator, and you end up with 735 units. All right. So there's that. There's your section 3.3.